All right, so we're going to talk about integrated rate laws. And the big difference between what we were doing before and what we are doing now is that in a rate law, remember it's like rate equals K times A. All right, this gives you reaction rate only at one point in time. Whenever it's that concentration, that's what the rate law gives you, okay? What the difference is in the integrated rate law, is the integrated rate law tells us what the concentration will be at any point in time. So it calculates the concentrations at different times. All right, so let's get on with it. So talked about zero order reactions. This is what I mentioned the other day. In the zero order reaction, the order is 0, right? So the rate law looks like this. Reaction rate equals K times the concentration of A to the 0, which I just already have up there, so I'll just do that. Equals K. So what does that mean? What's K? Constant. It's constant. That means reaction rate is measured based on the slope, right? So that means the slope is constant. And the only kind of line that gives us a constant slope is a straight line. And so when you look at the concentration versus time on a zero order plot, it's a straight line until it hits 0. Basically, it goes all the way until all the reactants are gone, and then it stops. Okay? Good? Good with that. All right, next. The integrated rate law for a zero order reaction looks like this. Y is the concentrations, right? B, right, because you know y is equal to, so let me write this out, y is equal to mx plus b. And that's true for this portion from here to here. When it gets to 0 and it flattens out, that's not y is equal to mx plus b anymore because it changes the slope. But y, right, is your concentrations. And then b, right, is your initial concentration. A0 is the initial concentration. So if you start with 0.1 molar, it would be 0.1 molar. In this case, it was what? What's the initial concentration here on the graph? 1 molar, right? So that's what A0 is for this graph. Now, if you're doing y equals mx plus b, right, you'll notice there's this is positive. So that means if this is m and x, then m has to be minus k. So what that means is if you measure the slope here, the rise over the run, right, delta y over delta x, right, that's equal to negative k. That's the negative of your rate constant. And then if you're thinking about what's x is the time. So there's your time, there's your y-axis. This constitutes what we call a model of the data. Right? It's a zero-order model of the data, which means if you have a zero-order reaction, it'll look just like this. Does that make sense? I mean, what's a model? Like in art. It's what you're trying to draw, right? All right. That's the expectation of what's going to be on the paper. That's a model. Does that make sense? Well, this is the model. This is what zero order looks like. So if you were to do the experiment today where you're measuring the concentration of dye as a function of time, right, and it wasn't a straight line, what would that tell you? Like if it is a straight line, what does it tell you? All right, concentration versus time. And you do the experiment, and it looks just like that.
It's constant?
Yeah, that is constant. It tells you the reaction's probably a zero-order reaction. Okay? If it's not like that, okay, you don't necessarily know what order it is, but you know it's not 0, because 0 has to be like this. So if it's curved, like a lot of the graphs I've shown in earlier slides, if it's a curved line, right, those were not zero order. Those were some other order of reaction. Okay. So then we also have first order and second order. And those are the only ones that we typically look at the integrated rate laws of. And I'm going to show you those graphs in a second. But I also want to tell you something that's significant about this kind of data analysis. If you wanted to know the order and the rate constant for a reaction, you have to run, up until now, you would have had to run lots of experiments. You do the rate and change the concentrate, have a concentration, then you change the concentration, you measure the rate again. And then you look to figure out what the order is, and then you plug the data in, and then you get the rate constant. You guys familiar with that process? We talked about it last week. You can say no. You can say yes. You can say something. Come on, let's go. No? Okay. So let's do this. So remember, we said if I have a generic reaction, A plus B, and it's going to C, I can write a generic rate law that says reaction rate equals to something, right? And it'll be K, right, times what? Concentration, right? Of, let's say, A, and the concentration of B. So I have to have the concentrations there. What else do I have to have? M and N, right? The orders. M and N. Now, let's say you wanted to know the order for A, right? You hold B constant, and you look at the reaction rate when A is changed. You guys remember doing that? Talking about that? We do 2 experiments. We do reaction rate change when B is constant. And most often, we doubled A, but we change A. Oops, it's not change, it's change. Change A. And then we determine the value for M. And so we had a reaction rate ratio. I'm just going to call it RRR, reaction rate ratio, okay? And that's going to be equal to a concentration ratio. And I'll show you how this relates to what we talked about last week. Raised to some power is a concentration ratio. So if I doubled the concentration, then double the concentration. Then the concentration ratio would be 2. That would be doubling it, right? That's the ratio. If the doubling of the concentration ratio doubled the reaction rate ratio, right? That means it's equal to 2. So remember we had all those tables of data and we looked at how one would change and then the other would change, right? And we said, oh, it doubled. Well, the reaction rate, that's the reaction rate ratio, really. It's the doubling of the reaction rate. So I would write something like this. 2 is equal to 2 to the n. And so n has to be first order. Something to that effect. And we did a lot of those last week, so this is kind of like a reminder. And I know we had a day off in between, that's like kills everybody. That Monday holiday. Should have it on Friday. Be better for me. Or like I think it said last week, we should have it on a Monday and a Tuesday and actually do something meaningful rather than, anyways. Yeah. 2 cents. Anyways. that's what I was talking about. How many experiments did I have to do that? I had to do 2, right? And I get the order for A, and then I have to do 2 more, and then I would get the order for B, and then I would plug the numbers in for one experiment, and then I would get K. So those were all the steps involved in figuring out the orders and the rate constants. But if you do it like this, let me show you something we're just talking about. Okay. If you do it like this, oop, that's weird. I think I want to just do this. Yeah. You can get the order from the graph because it looks 0 order, and you can get the rate constant from the slope. So really, you only have to do the one experiment to get that information. So it's more complicated doing this kind of analysis than going through and doing the ratios, but you get a lot more information out of it. Okay, you only have to do the one experiment. Okay, so I want to show you something really quick. See if I can pop it up. It should be one of my tabs. Yeah. See that okay? Good. This is what a first order and a second order concentration versus time graph looks like. Okay? Now, this one's first order. This one's second order. There's not a real good way to tell. I mean, they look very similar, but it turns out there are ways to graph these data that give you very significantly different appearances that you can just look at the graph and say, oh, it's first order or it's second order. Okay? And the same thing's going to apply when we graph this data a certain way, and I'll show you that in just a second. When you graph that data a certain way, it makes straight lines, and that's how we tell. Okay? Let me ask another question. Let's see how this goes. For first order, what's a rate law looks like? Reaction rate looks like. Reaction rate law looks like, for first order, right? K times A to the first. And somebody tell me, when we measure reaction rate, what we measure off the graph. Like if I'm looking at that graph, what am I measuring?
The initial reaction rate.
Yeah, usually the initial reaction rate, and we're looking at the slope, right? Because to get reaction rate, like I said, if I wanted to know the reaction rate for this graph here, then what I would have to do is, for example, take the slope between 2 points, and that's what I relate to the reaction rate, because the reaction rate is related to the slope through stoichiometry and some other stuff, right? You guys remember that? Reaction rate is the slope. What's happening to the slope on these graphs? It's decreasing as we go over time, right? That's what this equation actually is telling us here. Because it's telling us that because if you're looking at the concentration, what's the concentration doing over time? It's decreasing, right? So if this is decreasing, what it's telling us the reaction rate will decrease too, which means the slopes change, and that's why as it goes down, they flatten out, because that's the slowing down of the reaction. Okay? Now, you notice this is the second order, and this is the first order, right? Which one slowed down faster? Which one's slope is changing faster?
First.
Now you're looking at the slope. The first order is definitely steeper, but the one that's changing the fastest is second order, right? Because it's slowing down. You think about it, like if this was second order here, right? This is second order here. If it was going the same rate as this, it would be down here, right? But it's still high. And it continues to be high through the whole graph. And that's because, and you think about reaction rate, that's K times the concentration at A squared. That's the second order one, right? So as the concentration decreases, the rate slows down with the square of the concentration. So the slope changes faster, becomes slower and slower relative to a first order. For a zero order reaction, it doesn't slow down. That's why on this graph, right, a zero order reaction would look something like, see if I can do it with my phone as a ruler, would look something like this. It would just go straight to the bottom. Slope is constant, okay? All right. Next.
Did you ever have a third order?
Yeah, you could do a third order. They usually don't derive the third order equation, and that reason is more because you rarely come across those. A third order reaction generally means three things have come together at the same time and have the right orientation and enough energy to produce a product. And there's only a handful of reactions that are like that, like literally like you can count them on a hand. Most of the other reactions are second order, first order, or zero order. Have you had calculus?
No, but pre-cal,
Yeah. So in calculus, if you integrated, actually, so just a side note, a third order equation would look like reaction rate is equal to K times A cubed, like that, and then you just integrate that. That would be the third order rate law. And so this reaction rate is the change, for the calculus people, is the change in A over the change in time. And then you integrate with respect to time. Anyways, it's in the other notes. You can look at it. It's all set up, shows you how to do it. And then when you've had calculus and you think, oh, there must be an easier way, that's actually the easier way to do it. Right now, it's not the easier way. Right now, it's like there's two classes in front of you that and physics, same thing. If you know calculus for physics, makes life a lot easier. All right. Okay, so, some log math. I know people hate this. But we're going to just briefly talk about some of the math properties of logs because we're going to have to use them over and over again. You can refer back to this slide if you get stuck, but most of the properties you need are on this slide. Couple of things. What is a log, right? There are different kinds of logs. There's a base 10 log. Right? And traditionally, it's given that. Mathematicians would tell you it's actually this. And they're right. But if you look on a calculator, it doesn't have the 10 there usually. It just has log. Natural log is base E. So what does base mean, right? Base E. So that's the natural log. So let's talk about base 10 logs first and like what a base 10 log does, right? So if I have 0.01, right, that is the same as 10 to the minus 2. So the property of a log is that it returns the power of 10 that represents that number. If I take 10 to the minus 2, the power of 10 that represents that number is minus 2, and so that's why if you take the log of a number, it's that. For a natural log, the base is E. So if I take 0.01 and I take the natural log of it, right, it's going to return the power of E, whatever that is, and I'll tell you what it is that represents that number. So I have to get to my fancy scientific calculator because I keep forgetting to throw a regular scientific calculator in there. Well, they have reading glasses if anybody needs them. Sorry. Prescription though. So let's see, 0.01, and I'm going to take a natural log. That's minus 4.605. So that's the power of E that represents 0.01. So it's just like base 10 log. It does the same function, but it's a different base number. Okay. Now, why do people like logs? Right? Why do we use logs? Common reason given for chemists is it takes really small numbers and makes them into numbers that we can kind of understand. So, for example, 1 times 10 to the minus 14 in a base 10 log is just minus 14. So you don't have to keep track of all the exponents and stuff. It makes the numbers, it puts the numbers on a scale that we can sort of comprehend. But the other reason that people like logs is it allows them to do some interesting things with numbers using log properties, okay? Here's I'll give you the longer version of this. Before there were rules for long division and long multiplication, you know how when you stack two numbers and you multiply like 143 times 75 and you multiply by the 5 and you get a number, you multiply the 7 and you add a 0 and you get a number, and you add those together. Before they had rules for that stuff, they used logs instead. And the reason they would use logs is one of the properties of a log was something like this. If I take the log of A, and I just realized I forgot to put this one on here specifically, plus the log of B, that's the log of A times B. So when people wanted to get like the product of two numbers, they actually had log tables and look up the logs, right? And then they would add those numbers together because they could add, and then they would anti-log. They had tables for anti-logs, use the same logs to go forwards and backwards. Before calculators were invented. But it also led to some interesting mathematical properties. Okay. If you want to get rid of a log, you have to do the anti-function. And the anti-function for log base 10 is just raising that to 10 to the power of that number, and that gives you the number back. You can do it either way. You can say the log of 10 to the x. That ends up being just x. Okay, so the anti-log functions work either way. Another example, log of A minus the log of B, right, equals log of A divided by B. Just like if you add it, it ends up being multiplication. Long division could be done by just subtracting logs. And then another very useful function is if you have a to the x and you take the log of it, it allows you to rewrite it as x times the log of a, because the exponents can be brought into the front of the log of the number. Okay. This is all kind of review math, right? And kind of not, right? You probably were told this once and then never used it. Am I correct in that? Making that assumption? You've seen this before? Yeah? No? Yeah? Yeah. Hated it? Probably. Most people didn't like this part. They're like, logs. I didn't either, and I found out it's really important, so it's unfortunate. If you need to convert between base 10 logs and natural logs, you just have to multiply the base 10 log by 2.303. That number goes on forever. I think it's irrational. But you multiply by that, and you end up with the natural log of the number. So just so you know, there's all these different log properties. I'll just leave them like that, and you guys can come back to them. So what we're going to do is I'm going to use some of those log properties to get to some other equations you're going to need to be able to use on exams. So we're going to convert this equation form. Oops, sorry. Wow, I went really far. We're going to convert this equation form over here. I think it froze on me because I want too many things. Yeah, we're going to convert that equation into that equation. All right, so here we go. So when you do that, you're going to do this. You're going to say natural log AT minus natural log A0 is equal to minus KT. So I subtracted natural log of A0 from both sides, and that's what I ended up with. Okay. If you don't follow at any time that I'm doing this, if there's something like you don't follow, just tell me and I'll just explain it in more detail. And for this, we can use the log property. And the log property is that if I take the log of A minus the log of B, that's the log of A divided by B. So I'm going to end up with ln AT over A0 is equal to minus KT. That's a pretty handy equation, and we're going to use it later, right? But there's another one that comes from this. So that's this equation. The other one that's useful is to use the antilog function. So now we're going to take the antilog of both sides, okay? And so I'm going to get this, e to the ln of AT over A0 is equal to, remember, if you're going to do the antilog to one side, you got to do it to the other side, right? Got to do both sides, otherwise it's no longer an equation. Becomes e to the minus KT. What happens here? Log and antilog cancels, right? So this will cancel out like this. And so I'm going to have AT over A0 is equal to e to the minus KT. And then that usually gets rearranged into this form. So that's another important equation that you need to be familiar with. And the reason this equation is important because as it relates to the initial concentration, right, to any concentration later in time. So if you know the rate constant and you know the initial concentration, all you have to do is plug a time in here and then you can calculate the concentration sometime later. Wait, are you done writing? Sorry, I'll put that back up. It's only first order reactions that you run into that have all these equations in them. So you just got to get familiar with them. Try to remind me this week and I'll post the equation sheet for the exam, which is in 2 weeks. 2 weeks from Monday, I think. 2 weeks from last Monday. It's just on chapter 14. Right? I have an equation sheet for you guys to use. It doesn't contain every form of every equation, otherwise it gets to be ridiculously long, right? So, but you have to know how to convert between different forms. Wow, played it through that. Well, I don't want sound, so how's that? I gotta shut the sound off. Let me go back up here. Okay, second order reactions will look like this, right? What's N in a second order reaction? 2, right? So this will be 2 for second order, right? It's the same equation form, you just change the order. When you integrate, you get a different equation. What's that? Oh, yeah, like A and B. Yeah, I'll show you how to deal with that later, but for now, let's just assume the reaction just looks like this one in the top right-hand corner. Just A goes to B. So I'm only dealing with one reactant. If you have 2 reactants, you have to do 2 experiments. Okay? So you have to do 1 experiment to determine the order of every reactant. Okay. Yeah, and I'll talk about when we're going to go over there and do the experiment for the dye. There's actually 2 reactants. I'm only having you figure out the order of 1, but there's an easy way to figure out the order of the bleach. I'm having you do the dye from a graph. So we have a reaction of dye plus bleach makes some unknown products. Actually, nobody really knows what they are. If you read in the literature, we're like, well, we can do this experiment. We don't really know what all the products are, right? Because we know the reactants. And I can tell you how they determine the order for the bleach, even though we're not doing it. It's actually a simple experiment, but we're not going to do it today because it adds another level of analysis complexity that I don't want to get into. Okay, so that's the integrated rate law. So let me point something out to you real quick. This equation is y is equal to mx, and this is b. So that means if you take and make a graph, and you put time on this axis, right, and 1 over the concentration on this axis. So you're going to do an experiment, you're measuring concentration, and you're measuring at different times, right? And then what you do is you graph it as 1 over concentration over time. That guy there versus time. What you'll get is a straight line. And the straight line is going to have a positive slope. And it's going to have an intercept. And the intercept is going to be 1 over A0. Now, typically, you know what A0 is, but it'll graph a line that should meet at the same point. And you'll have your data points will be on top of this line. The slope that you measure off of this line is just equal to the rate constant. So let's say you do an experiment. I'll throw this out there, see how you guys pick this up. And you don't know the order. And the order is either 0 or second. For some reason, you know it's not first. Okay, because I've only told you the linear forms of 0 and second right now. I haven't talked about first order yet. But let's say you do this experiment. Make a new chart. And you measure concentration and time. So you make a table of data like this. And you have, different times and you have different concentrations. And then you graph it, right? And the data is either 0 or second order. And you graph it like this. You say A versus T. That's known as a zero order plot. This is the concentration graphed as time is known as a zero order plot. And then you also graph 1 over A versus time. So this is zero order, and this is second order. So you can take the same set of data, you don't know the order, right? And you can graph it 2 different ways. If it's zero order, which one of those 2 graphs should be a straight line? The zero order one, right? If it's second order, which one should be a straight line? The second order one will be a straight line. So think about it like this. We have a set of data, and we don't know what the order is. So what we're going to do is we're going to graph it 2 different ways, which is literally in a spreadsheet. Just dump 2 different graphs out from it. And we're going to look at the graphs, and we're going to say which one's a straight line. And the one that's the straight line is the order, is telling us what the order of the reaction is. And as it turns out, if it's a straight line in one, it's not going to be straight in the other. It'll definitely have a curve to it. It'll have like an upward curve or a downward curve. So if I graph it and it looks like this, then that'll be a zero order reaction. But the second order one will do something like this. It will not be straight. And that'll tell me zero order. And then if I want the rate constant, it's the negative of the slope. On the other hand, if I graph it like this, right? And goes like this, and then this one's going to go like this, then it's second order. Two different possibilities with two graphs. All your data points will fall on this straight line. Now, the straight line won't be there magically. You have to add it to the graph, right? You have to tell Excel, actually we're doing Excel, you have to tell Excel, add a trend line, it'll add a trend line, and it'll sit on top of all the data points. And from that, we can tell what the rate constant is, because for second order, the rate constant, that's K, is the slope. All right, does that kind of make sense? You get your data, you graph it two ways, whichever gives you a straight line, that's the order for the reactant. And the slope is derived, the rate constant is derived from the slope. Well, it turns out, okay, I'm going to show you another one now. For first order, we didn't talk about this, but it was on the screen. Natural log of AT equals natural log of A0 minus KT. Y is this. B is this. Oops. And this is MX. So your slope is equal to minus K. B is your intercept, right? And this is you're going to use for your X values, you'll use T. So now you have three different ways to graph the data, adding this into the mix, okay? You're going to get a set of data. And this is time. This is concentration of A. You're going to have the natural log of A. And you're going to have 1 over A. Like that. And you'll calculate all those values. Now, you guys familiar with how spreadsheets work? Because that's one of the things I'm going to teach you. Actually, I'm going to teach you how to do it, and I have videos on how to do it on my YouTube channel. But I think I linked the video directly into Canvas. It tells you how to do it. All you have to do is type the equation once and then copy and paste it. It does all the other calculations for you. Okay. So basically, you type the equation once. This is how I do it. I check it on my calculator to make sure it's okay, that I didn't type the wrong function in. And then you actually grab the corner and you drag it down, and it fills the entire box with the equations. And then you just graph it. So one of the things I'll show you how to do, and I think I set aside next Monday for that, and then next, and that's not going to be the whole class period, but that'll be part of the class period, getting your data. Today we're going to collect the data and we're going to get it into Excel format, and then you guys can watch the videos and maybe get ahead of me on this, but on Monday you guys will actually be doing it as part of the lab plus a study guide for chapter 14. We'll start then, and we'll study for the exam on Thursday, and then, on Wednesday, and then following Monday will be your exam, okay? Just a quick overview. I haven't got all the calendar stuff in for 1B yet, but I'll get it all in there, and you'll see all the dates and stuff and when everything's due. It'll be a little intimidating, but I'm pretty easy with due dates, by the way. Okay, so you're going to take one set of data, you're going to graph it three different ways. So you have three graphs that come out of this. This will be A, this will be ln of A, and this will be 1 over A. And for all of these, you'll have time as your x-axis. This is my zero order model, so I'm just calling it mod 0, but that actually means something else in math, so don't say that out loud by a mathematician or a computer scientist. This is mod 1, and this is mod 2. Okay. I'm going to take the data, I'm going to graph it three different ways, and it should be pretty apparent to you by looking at the graph that one of them is a straight line. How do you know when you see a straight line? I mean, you just know, right? You look at it and it doesn't curve. My PhD advisor, I'd hand him a graph and he would do this. He would take the graph and look at it. He had a big mustache. He would always do this thing with it, which makes me crazy, so I'm trying not to do that. And then he would just hold your graph up like this, and if it's a straight line, all the data points are in a row, right? And that's what he did. So you can actually just do that with this data. You can actually see that it's a straight line. And then from that, you'll get a rate constant, right? And that's the gist of the experiment this week. We're collecting the data for that. Okay. So let's use this equation, one of these equations. It says, and show how the calculations work. And I'll do one for first order, one for second order. This is the second order one. So it says a second order reaction, right? Starts with this concentration. And then it says what or how much A remains after 450 seconds. And it gives you a rate constant. So first there's things that you have to do. One, you have to identify the important information. Everybody seems to be able to find the numbers. That's no problem. This is also important. Second order reaction tells you got to use the second order equation. And then you're going to have to remember what that is or be able to find it on the equation sheet. Okay. And that's going to be 1 over AT is equal to 1 over A0 plus KT. And then we just have to identify all the variables. So T, that's the 450 seconds. K, that's a 4.0 times 10. I think that's minus third, right? Minus third, yeah. On my iPad, it's not showing up. Molarity to the minus 1, seconds to the minus 1. And I have an A0. And that is 0.500 molar. And AT is what I'm trying to find. That's my find. So I have all the variables. I can plug them in. I'll plug them in like this. 1 over AT, that's what I'm finding, is equal to 1 over 0.500 molarity plus 4.0 times 10 to the minus third molarity to the minus 1 seconds to the minus 1. That's K, and T is 450 seconds. Now, if you take a second to the minus 1 and a second, you multiply them together, what do you get? They cancel, right? So those will go away. And so I'm going to say 0.004, because I don't have my scientific calculator, times 450. That's going to be 1.8. Units are molarity to the minus 1. And this is going to be 2.00 molarity to the minus 1. So I just have to add those together. So I get 3.8 molarity to the minus 1. And then to solve for A, I have to take the inverse of both sides. So AT is going to be 1 over 3.8 molarity to the minus 1, which equals, actually it says on the slide, .263. I think it actually comes out to 0.262. I think I checked it yesterday, but molar. Last thing you want to do, go ahead.
Where did you get the 2.0 molarity?
Oh, I inverted 0.5. Yeah, I took 1 divided by 0.5. And then down here, it's in molarity units, right? So then it's molarity to the minus 1. Yeah, I just divided the unit. But that's a good question. A lot of people get this 3.8 and they stop and go, oh, that's the answer. They forget that the other side of the equation is 1 over. And they're just like, And if it's on a multiple choice, you know both answers will be there, right? So be careful about, make sure you check your units, finish your calculation. The last thing you have to do is you have to check to see that it makes sense, right? So I started with 0.5, right? And over time, you expect the concentration to go down, right? So as long as your answer is lower, at least it's headed in the right direction. So that's about all that's the only way you can really check this right now. Just look to see if the concentration is lower than what you started. You can also plug the numbers in and see if you get like the left side, right side equal to each other. So there's other ways that you can do it. Okay. Let's try another one. It says a first order reaction starts with 1 millimolar A. How much A remains after 50 seconds? Okay, so relevant information, right? What's important out of all this? You have 1 millimolar, you have 50 seconds, and you have the K. What's the other important bit of information? It's first order. So you're going to need a first order reaction, right? So the first order equation, I mean. So here's the thing. There's a lot of different forms of the first order equation. What are you trying to find? Probably a concentration, right? It says how much. So started with the concentration. You want a concentration at the end. So what you want to use, actually, there's different forms of the equation. You want to use this one. Because this is the one that gives you concentration as an answer. The other one's the natural log of the concentration or the natural log of the ratio of the concentration. Those just don't apply. Okay. So you find the order, and then first, the case of first order, you got to find the equation that best suits the kind of calculation that we're going to do, and then it is a plug and chug. It's actually like it's been called. Just throw the numbers in there. So A0 is 1.00 millimolar units. You're going to find that I like milli maybe more than I should. Hopefully you'll learn to love milli like me. K is 2.6 times 10 to the minus 2 seconds to the minus 1, or inverse seconds. All right. And then time is 50 seconds. And then we got to plug these things in. So we'll say AT equals 1.0 millimolar. The units of concentration don't matter in this calculation. Whatever unit you end up with, that's what you'll end up with in your answer. Okay. And then it's going to be E. Now on your calculator, this is one of the reasons why I'm doing this problem, you'll have to look for an E or to the X or an EXP. Sometimes it's EXP with an X. So there's different functions. This depends on your calculator. And then you're going to take E and raise it to this power of negative 2.6 times 10 to the minus 2 seconds to the minus 1 times 50 seconds, like that. And then again, seconds to the minus 1 cancels with seconds. So let's see what that comes out to, that exponent. I get 1.3. So I'm just going to rewrite this. Should end up with something like that. And you do that, and you should end up with 0.272 millimolar, or 2.72 times 10 to the minus 4 molar. And I gave you another option on the slides as well. Any questions about the plugging in and doing all that stuff? Functional stuff. All right. All right, so next section that we're going to talk about is about reaction half-lives, and just about enough time to cover all of this, I think. One of the ways we analyze data is by looking at how long it takes to get to 1/2 of the initial concentration. So let's say that opening the doors just keep popping. I think it just doesn't want to shut. There you go. Oh, now it's just going to hiss all the time. Okay, let's say you start with 1 molar, right? What's the concentration after the first half-life? Start with 1 molar. After the first half-life, how much do you have left? 0.5, yeah. So that's what I just wanted you to get that idea. It's actually a number, right? So if I start with 0.3, right, then after the first half-life, it's 0.15. It's half of the 0.3. Okay? Whatever that time is, it turns out that time it takes to get to different half-lives is characteristic of the order of the reaction. It tells you something about the reaction, and also, if you know the order, the half-life tells you what the rate constant is. Okay? So we're going to derive these equations so you can see what they are and where they come from, and then we'll see how we use them. Okay? So half-life is the time necessary to reduce a concentration by a factor of 1/2. Its symbol is T1/2. Right? And every order has its own equation. So there's 3 more equations we're going to have. They're going to be on your equation sheet most likely. I can't remember if I put them on there or not. All right. And they come from the integrated rate law. So what I'm going to show you in this next bit is how you get them from the integrated rate laws. So this is the equation for first order reaction. It's the one that's easiest to work with. Okay? So let me ask a question. What is the ratio if T, okay, let's take some time to think about this. If T is equal to T 1/2, what's true about that? That's AT divided by A0. Now, A0 is your initial concentration, right? And AT is the concentration at the half-life. What is that? It's a number. What? 0.5. 0.5 is half, right? The concentration at some time divided by the initial for the half-life is always going to be a half. So this is 1/2. Now, there's other ways to get to that, and I'll show you that in a second. Or 0.5. Right? Other ways to get to that. But it goes something like this. Then I have the natural log of 1/2 is equal to minus KT. And because I said it's the half-life, right, now T is T 1/2. Anybody know the natural log of a half? Nope, you don't. Pretty sure. I don't know the natural log of a half. I jest at that a little bit. I've seen it enough times that I kind of know what it is, but I always forget. I'm going to simplify this equation one more time, though. I can also write natural log of 2 to the minus 1, because that's equal to a half, is equal to minus KT 1/2. And this is minus natural log of 2 using one of those log functions, right? Pulled the exponent out, brought it in front. So now I have, what can I do with the minus signs? I have to cancel, right? So I can get rid of them. And so I can say natural log of 2 is equal to kt 1/2. And if I want an equation to relate to half-life, I can say t 1/2 is equal to the natural log of 2 divided by k. I could write that the other way too. I could say k is equal to natural log of 2 divided by t 1/2. And 6931. That's what the natural log of 2 is.
Is it negative?
No, because it's not negative because it's not a half anymore. I just turned it into 2 and got rid of the negative. Yeah. 6931? I don't know. Times k. All right. So let me ask a question. And I'm going to expect that you'd be able to do that. Like on a test, I might say, show the short derivation for first order half-life. All right. So you have to think about the steps involved and the substitutions and how it cancels. But it's not that hard. Part of that is to get you really familiar with some log functions. Part of it is it's just the expectation in Chem 1B that you'll be able to do some of these things. So let me ask a question. Okay, so the answer to this is going to be obvious, so don't think too hard about it. Okay, it's so obvious that it's not obvious. That's the problem. How does the half-life depend on concentration? Do you guys see concentration in there? Do you see concentration in there? Right? No, it doesn't depend on concentration. That's the answer. The half-life doesn't depend on concentration for first order. If it depended on concentration, concentration would be in there. So there's an interesting thing that happens, okay? I'm going to draw a concentration versus time curve, okay, for a zero order reaction based on that idea. So I'm going to make a graph. Let's go like this. It's my y-axis that's curved. Here's my x-axis. Name a favorite concentration other than 1 and not 2 either. 7? All right, 7. That's my initial concentration. Let's say this is my first half-life. And we could calculate what that value was if we knew what K was. Okay? What's the concentration at the first half-life? 3.5. So that's about here, right? Oh, maybe not. So I've already got 2 points on my curve. My initial concentration, which is 7, and my concentration at my first half-life. Can't get this thing to draw a dot. There. Oh, that's 2 dots, unfortunately, but let's try and make 1 dot out of it. Now, that now becomes the new initial concentration. If I go out another half-life, and remember, half-life doesn't depend on concentration, so it's exactly the same as the first half-life. Right? What's the concentration at the second half-life? And you could say like what it is mathematically. Yeah, 1.7, 3.5 divided by 2, right? Visually, it's halfway here. This is 1.75. And let me do a third half-life. And then, again, because you picked 7, now you have to take 1.75 and divide it by 2, and I'm just going to say it's here. Because graphically, you can just keep splitting it by halves, and that's the concentrations at the half-life. That's here. And the graph looks like this. So now you get a set of data and you look at it and you say, oh, what's the first half-life? Now, how do you know what the first half-life is? Right? Collected data. Today you're going to collect data. And you're going to look at the first half-life. How do you know what the first half-life is? Take the initial concentration, divide by 2. There's your first half-life. Then you're going to go, what's my second half-life? Right? You take that concentration, just on the graph, and divide that by 2 and move across. If those two times are the same, it's first order. If you have multiple half-lives in your data, you can just look to see what's my initial concentration, what's the time to get to half, and then you go, I go out half that same time interval again. So on like this graph, you're going to go out that same time interval again, just out here, and say, what's this concentration do? Right? And if it's about half, then it's first order. It turns out if it's second order, it won't be that. And if it's zero order, it won't be that. Each one has a different shape to its graph. Like I showed you in the beginning, zero order goes straight down. First order has a curve to it. Second order has a curve to it. But those curves have very specific shapes. And you can tell the orders of your data by looking at those curves. Okay, questions about that? You guys kind of pick up on all those sort of the relationships between half-life and how you tell if your data is first order, that kind of stuff? Okay. That's a first order graph. Again. So let's try something else. Let's say that that's our data, right? You can tell that it's first order because if you keep doing the half-lives, right, like I said, it's always the same distance to half the concentration, so the time is always the same. Now let's say you want to calculate the rate constant. I want to say, what's K for this reaction? Then you can say, well, the half-life, what does the half-life look like it is? Well, you have to kind of measure it, right? And what does that look like to you? There's 1,000, there's 2,000. This is not quite all the way. It's like 1 point, what? Eyeball it. What do you think that value is? 1,500? Because the 1,000's right here. You can't quite see because I got to change this so that the line's going vertically or black instead of white. Yeah, I put a background on it. So there's 1,000, there's 2,000. It's not quite halfway. So I would say it's like 1,300 or something like that. So that's about 1,300 seconds for the half-life. If you want to get a little bit closer, you could do the estimate for like 4 or 5 half-lives and divide by 4 or 5 or whatever you do. Okay, that's about 1,300 seconds. So K, I know that T1 half is equal to the natural log of 2, which is that number which I can never remember, divided by K. So K is going to be equal to the natural log of 2 divided by T1 half. And I can just calculate that value. Okay. So, 0.6931, is that what it is? 0.6931 divided by 1,300. And that's going to be 5.3. Times 10 to the minus 4. And the units, there's seconds here, and I'm dividing by time, so it's seconds to the minus 1. Okay. I'd like to look at second order, too. We have enough time to look at second order, so we'll look at...
I can't read your handwriting. Is it natural log of 2 over T?
Yeah, natural log of 2 over T1 half. Yeah.
1/2.
Yeah. That's what happens when I don't zoom in and write too fast. If I zoom in, it's a lot easier to write smooth than I'm way out. It doesn't matter what I draw, it's always nasty. All right, questions? So that's the one way that you can use the equations. If you know that you can look at the data and you can see the order in it, then you can use the half-life equation to calculate what the rate constant is for the reaction. So we've come up, and we'll summarize this in the next lecture, we've come up with like 3 different ways now how to determine the order and the rate constant. Okay? And so we're going to have to sort of write all these things out. And so in the next lecture, when I start, remind me, I like to make a big table and list all the things that we've learned about determining orders and rate constants. Okay. Oh, yeah. And then, it allows you to quickly determine K from experimental data. Given the first order reaction and a rate constant, it allows you to graph it quickly. And then the last one is it's on the test. So people always ask me, why is this important? Because it's going to be on the test. That's all you really need to know. Okay. I'm going to skip this one real quick. I already did a sketch already, so I'm going to talk about second order. I'll come back later and I'll do some of those other examples if I have time. Second order. It's a little bit trickier to get the equation out of. But one of the things that you can say is that AT is 1/2 A0. So this concentration is half the initial. And again, I'm going to make T equal to T 1/2. And then there's a little bit of algebra after that, arithmetic, algebra, it's algebra. So that's 1/2 A0 equals KT plus 1 over A0. And T is T 1/2. So I'm going to rearrange this. I'm going to get KT 1/2 to one side. And I'll get the A terms together. So it's going to be 1 over A0. Oh, sorry, 1/2 A0. So I'm switching it like this, flipping the sides. Minus 1 over A0. So I flipped the equation and I brought the A0 across. What's this become? What's 1 over 1/2? 2, right? It's 2 over A0. So I have K T 1/2 is equal to 2 over A0 minus 1 over A0, and that's just equal to 1 over A0, right? That leaves me with this equation. K T 1/2 is equal to 1 over A0. And if I want a half-life equation, then I'm going to do this. T 1/2 is equal to 1 over K times A0. And you notice what's really different about this equation. It has a concentration in it. So in second order reactions, the half-life depends on whatever the starting concentration is. And unfortunately, I didn't leave room on this for a graph. I want to draw a graph of it. So let's draw the graph. I'm going to take this equation, and I will take it to a blank slide. Okay. There's my equation. I want to graph it. So here's T1 half. So 1 T1 half. That's another T1 half. It's another. So I didn't calculate T1 half. I'm just saying relative to T1 half, right? So I'm going to pick the favorite concentration this time. Sorry. I'm going to make it 1. I get to choose 1 because I'm the teacher. What's the concentration at the first half-life? 0.5. Yeah, it's half, right? So I got a point there, and I got a point there. That part of it looks exactly like first order. But this is where it changes. If this was my A0 for the first half-life, but now this is A0 for second half-life. Your initial concentration for this half-life equation just depends on which half-life you're in. For first order, it didn't matter because it wasn't part of the equation. But for second order, now it matters. Now, if this number, right, is half, what does T1 half do? If that number is half, then what does T1 half do? It'll double, be twice as big. Because if I divide by a number that's half the size, then the result will be twice as big. And so the next half-life is actually this long. That's the second half-life. It's twice the original half-life. The concentration is still half of the original, like this. And that trend will continue. Every time you get to a half-life, the half-life doubles. So the next half-life will be 1, 2, 3, 4 of the originals, and it'll be down here. And the curve is going to go, oops, whoa, I didn't mean to do that. The curve is going to go something like this. And it slows down rapidly because of the concentration's effect on the half-life. Okay? All right, I'm done.